Previously, we talked about what an epsilon-NFA is. We talked also about how it computes on an input string. Now, I want to address a fundamental question now. Is if I give you an epsilon-NFA, is there a corresponding deterministic finite automaton, or DFA, that recognizes the same language? And the answer is yes. Yes, there is. And what we can do is we can actually take what we discussed previously about the subset construction and incorporate the aspects of the definition of the epsilon-NFA into it. So we're going to talk about how we can take an epsilon-NFA and get a resulting DFA that recognizes the same language. So we'll talk about epsilon-NFA to DFA conversion. So we're going to be taking the version of the subset construction we had, namely the lazy counterpart we discussed previously, and we're going to be adapting it with the definition of how an epsilon-NFA computes. So if you notice this, it's a piece of cake. So if you understood the subset construction, this modified version, which is much more general, by the way, because every NFA is an epsilon-NFA. It just doesn't have any epsilon transitions, right? This is a much more generalized way of me talking about this. So naturally, we can also employ a modified version of the, and I'm going to presume it's the lazy counterpart, but you can easily see it in other circumstance. So I'll define it first in the way that we talked about previously. Modified version of the lazy subset construction to build a DFA, D, which is going to be equal to QD sigma. Its input symbols are going to be the exact same. Delta D, QD, FD. So the subscripts I'm just using to denote those associated with the DFA. From an epsilon-NFA, E, which is going to have states QE, sigma, delta E, Q0, FE. So just like I did for the subset construction and the lazy counterpart, I'm going to first talk about what we're going to have each aspect of this DFA be. So we're going to talk about what the states are. We're going to talk about what the transition function is going to look like. We're also going to talk about any other little wrinkles, like even the start state. The start state might differ, right? So let's first talk about the states. So the states. So it's going to be a set of subsets S, which are going to be a subset of QE, where each S is going to be the epsilon closure of S. So the technical term, by the way, for this is that this is often referred to as the epsilon closed subset of QE. That's what this is referred to as. Note that if it was empty, then the empty set is also an epsilon closed set as well. So essentially, I'm just saying, hey, look. So for each one of the subsets, you'd imagine you have the epsilon closed version of it. So QD, so this is the set of states for the DFA. can be constructed by beginning with the start state QD, which I'm going to define this below. So I haven't defined what QD is quite yet. So you start at QD, and until no new states are discovered, akin to the lazy subset construction, are discovered as a result of following transitions, add any new states to QD found as a result of combining the lazy subset construction. We previously discussed this for NFAs with the transition computation below. So I'll give you that in a moment. But this shouldn't be terribly surprising. So it'll look a lot like the lazy subset construction we had before, just with just a couple wrinkles. So next, we're going to need to know what the start state is going to be. So any suggestions of what the start state should be? What's the start state? Let's think about it. What would be the start state? Well, think about it. If you had Q0, which is the start state of the of the epsilon-NFA, what would it be? So what subset, which remember in the lazy subset construction, this would be a label that represents a state in the DFA. What would it look like? Would it just be Q0, like in a set? No, it won't necessarily be that. It'll have to be all of the states as a result of the epsilon closure on that start state. So QD, so this is what I was referring to as being defined below. So it's going to be the epsilon closure of Q0. So whatever that subset will be, whatever that is the start state. So this, whatever this is going to be the label for that start state for the DFA. Final states. Let's talk about the final states. The sets of final states, which remember, these are labels. They're states in the DFA. Is of a final, sorry, it's the set of not final states, the set of states that contain at least one accepting state. Of E. So all of those subsets, they're final states, which is not terribly surprising because it should remind you of the subset construction, as per usual. So now we got to talk about transitions. And this is really kind of the big wrinkle other than what we talked about just above for the start state. And just generally how this works, where we're going to have it where wherever the set of states would be, they're going to be resulted versions for which we apply epsilon closures. This is where this mechanism is going to play out, as I discussed previously. So for transitions, we're going to let set S be P1, P2, all the way up to PK. And we're going to define delta D for, remember, this is going to represent a label, but it is a subset when we think about it in terms of the context of the epsilon-NFA. So S and A is computed as follows. So this should first remind you of the subset construction, just vanilla with an NFA. So one, you're going to compute just as per usual each of these transitions on the symbol A. You get these, lump them all together, and they'll end up with some set of states, right? It's some subset. So let the result be, I'm going to call them R1, R2, all the way up to some state Rm. So that's the first step. That shouldn't be very surprising. This is just what you would do in the subset construction, correct? As per usual with an NFA. But now we have to add in the part that makes this unique to an epsilon-NFA that contains all NFAs, but this second step isn't terribly interesting for just an NFA. Okay, delta D S A is going to be equal to the epsilon closure, or E-close on this set, the resulting set, as we've described previously when we talked about how an epsilon-NFA computes, right? So this is actually how we can describe the DFA. So I think it's a good idea we see an example of us carrying out this lazy subset construction on an epsilon-NFA to produce a DFA. So we're going to consider this epsilon-NFA. This is going to be epsilon-NFA E. And what we're going to do is we're going to produce a resulting DFA that's going to accept all strings that this epsilon-NFA accepts. Just for context, I thought it would be a good idea I show you just what the transition table for this would look like. So just for completeness, I gave you the transition table and the transition diagram for NFA E here. So let's try applying the modified subset construction, or more broadly, a subset construction to this epsilon-NFA. So what would be the start state of the resulting DFA? So for DFA D, what's QD? So what did we say the start state is? It's the epsilon closure of the start state in the epsilon-NFA, right? So the start state, so what would it be? So let's see. This is going to be the epsilon closure of Q0, which in this case, that's 0. But that's just simply 0, 1, 2, 3, and 5. I was about to put 4 in there, but yeah, it's no 4 in there. So this is the start state, is this subset, which is a label for that state. Now, we're going to go through this process of applying the lazy subset construction. So just to make this easier for us, I'm going to include a table here. And we're going to fill this in as we discover new states. So we know that the start state is going to be is going to be this one. That's what QD is. So now, let's think about this. How are we going to proceed now? So if I give you this subset, we have to use the transition function to figure out what's happening on each one of the input symbols. So if I apply it on A, what should it look like? Well, what would it be? Well, the definition, so remember there's two steps. First, we figure out all the set of states that you would transition to on A from each of these. Then you would apply the epsilon closure to that. So to figure out delta QD, so I want to figure out delta QD. Now we got to go through all of these and apply the transition function. The resulting ones let's see. 1A, two A, I'll get out of the way in a moment, 3A, 5A. So whatever the resulting label will get or subset will be the result of considering this. So what are we looking at for each one of these? So for state 0, so let's look at our table here. It might help us a little bit. That's empty, right, for 0 on A. 1 on A. 1 on A. That's nothing. 2 on A. 4. So far we got a set that contains 4. So that's 2 on A, right? So this one you have 4. All of these are empty so far. 3 on A. That's empty. How about 5 on A? That's empty. So the result of this is 4. Now, so that's the first step for what we're going to determine this cell of this transition table will have. What's the next step? We have to apply the epsilon closure on this. The epsilon closure of this state, because you go through each one of the states, you take and put them all together. So, epsilon closure of state 4 is 4 and 5, right? And naturally, that's exactly what would go in this cell for the transition table. So, the same idea as we had before, except you're going to have this new step where you're just going to apply the epsilon closure. Otherwise, the process is the exact same. So let's see what else we got going on here. So just don't forget about that second part. So let's think about B then. So for all of these states, let's go through the same process now with B. So you just do all of these again, but now with B. Well, let's look at this. Okay, 0 with B. That's empty. 1 in B. Empty. 2 in B. Empty. 3 and B. 4, again. And 5 on B. We got 5. So now we have 4 and 5. That's what the result would be in this case, because I take the union of all the results there. Then I apply the epsilon closure on 4, the set containing 4 and 5, but that happens to also be the exact same set, 4 or 5. So now that we've discovered a new state, namely this subset, we're going to add a row for it. And now let's do the same process. So next, we've got to consider all the transitions on A. So let's think about it. Let's try to do this a little bit faster this time. Say 4 on A. 4 on A. Okay. If I just consider 4, that's nothing there. 5 on A, nothing there. The epsilon closure of the empty set is still empty set. How about for B? Well, the transition for 4 on B, and nothing. On 5 on B, it stays in 5, right? But the epsilon closure of the set containing 5 is just the same set. This is technically a subset, hence we need to write a row for it. It's the one I next discovered. Well, this row is really easy, right? So it's just empty everywhere because notice there's no set of states, and for all of them, I'm just going to end up with another empty set. Taking on the epsilon closure of that set is still an empty set. That means now I got to consider this next discovered set of states. This one right here, I haven't accounted for that one yet. I'm just doing it in the order I discover them. So now I have 5. Okay, 5 on A. There's no transitions on 5 with an A. So you know right away that the epsilon closure is definitely not going to introduce anything else, because there's no epsilon transitions out of 5. And it's not transitioning on A at all, right? So if you're not convinced by this, just go through the same set of calculations that I did over here. Okay. Now we got B here. So B, 5. What happens? So on a B, if I'm in state 5, I stay in state 5, right? But there's no other states. Then I apply the epsilon closure onto that set of states, which just has 5 in it. It still contains 5, nothing else though. Have I discovered any new states that I have not accounted for with a row? Now, I've got them all. But there's one thing I did not account for quite yet. What are the final states? Well, as per our discussion, as long as it's a subset that contains at least one of the final states of the epsilon-NFA, we're good. So, notice that this one has a 5 in it, that has a 5, this has a 5. So, this is the final state, that's the final state, this is the final state. And then once you're done with this, you're welcome to relabel the states if you would like, rather than working with subsets. But let me draw the resulting DFA. So this is the resulting DFA from the lazy subset construction applied to this epsilon-NFA. So please note that the main differences are when you come up with the start state, it has to be that it's the epsilon closure of whatever that state would be, as opposed to before it would just be the set containing the start state of the of the NFA. Next, final states, same concept. Contains one of the at least one final state. It's got to be one of the final states. Not much different. No. The main thing that is different, other than just the way the start state is defined, is how you determine each one of the transitions. It's 2 steps. The first step is exactly the same as it would be if you applied the subset construction to an NFA, but it has a second step where you just apply the epsilon closure to that set of states before you put it in that cell. So that's just an extra step you have to do before you put it in the cell. And you might ask, Dan, why do you do that? It's because that's the definition of how it computes. So if you miss out that step, you're not working with an epsilon-NFA anymore, you're working with just a vanilla NFA. And that's why that second step exists. So, because you need to have it where you allow it to go on those epsilon transitions to incorporate any states that it is able to reach via epsilon transitions. So, this brings me to an ultimate question. Ultimate question. Ultimate question. Do epsilon-NFAs give us any more computing power, as in it recognizes more languages than a DFA? Well, let's talk about this now. So I'm going to give you a little sketch of where I'm going with this. So just to summarize where we were before, remember that we talked about this a little bit. Is that previously we had shown that if I give you an NFA N and has a language N, we can use the subset construction or its lazy counterpart to create a corresponding DFA D, where its language is L of D, where these two languages are in fact equal to each other, meaning that there's an equivalency between these two models. So for any DFA, I could construct an NFA, and for any NFA, I could construct a DFA. So there's an equivalency. Now, it should be not very surprising at this stage, given that I've given you a process that converts an epsilon-NFA to a DFA. Its proof of correctness is very similar to the one that I did for the NFA to a DFA. That's why I'm not going to present its proof here, because the proof is nearly identical. Just you have to incorporate the transition function and those couple little wrinkles that come with the epsilon-NFA's definition. Other than that, the argument is the exact same. So that's why I'm not going to prove it here. But it's also worth noting that every DFA can be recast as an NFA, where its set of transitions always consists of one state, right? So technically speaking, there's a very trivial way of going from a DFA to an epsilon-NFA, because every NFA is an epsilon-NFA. The only technicality you have to watch out for is that when you define it akin to our transition table over there, is that I need to define transitions on epsilon, all of them, appropriately. So if I have it where you're allowed to have these epsilon transitions, well, what do you do with them? Well, they don't go anywhere, right? So but that's the only technical detail. Other than that, you're just dealing with a vanilla NFA again, right? And you just apply the basis for the NFA definition for when you read an empty string, right? So that brings me to the question. Okay, so now we know that if I give you a DFA, I can give you a resulting epsilon-NFA. So I could may as well just put this here. And now you can go from the epsilon-NFA to the DFA as per the lazy subset construction, or just the subset construction more broadly. You would just apply the epsilon closure for the second step as per the subset construction before. You can go from here to there. So that gives me the point of describing the next theorem to you. So, similar to before, so that's doing a lot of heavy lifting here, but similar to before, epsilon-NFAs are equivalent to DFAs. They recognize regular languages. So I'm not going to present the full proofs to you, but like I said, the arguments present are nearly identical. You just have to add in the couple wrinkles for defining things such as the epsilon transitions, and in the part from the subset construction, you would just add in the parts involving the new start state and the fact that you have it also where you employ the epsilon closure. Other than that, the argument's the exact same. So anyways, this gives us our theorem here, the big theorem for today. So a language L is recognized by a DFA if and only if L is recognized by an epsilon-NFA. So that means that the epsilon-NFA does not give you more ability to recognize other languages other than what we had for the DFAs, akin to the NFAs. It just gives us a richer feature set for how we can design these machines.